Today we have a Fiona Burnell who will talk about higher rank chirality in semi-metallic system. Please.
Great. Yeah, thanks. So I should preface the talk by saying that I apologize if there's background noise on my end. Our childcare does not start until 9 a.m. Central, which coincides with the end of my talk. So just to warn you guys, if that does happen. Okay, so yeah, so today I'm going to talk about, mostly about topology more in the kind of band theoretic sense. And so this is some work that I have done / am doing with Taylor Hughes and his student Oleg Dubinkin. Okay, and so, whoops, here we go. So yeah, so the talk is kind of divided in two parts. So in part one, I'm going to tell you about a sort of connection to fracton-like physics, okay, which I'll explain a bit more about what that means in a minute. But basically an analog in systems with a kind of subsystem symmetric or higher rank description of the chiral, or perhaps more appropriately, the axial anomaly, which is familiar from 1+1 dimensional, sort of QED. And then, as we know, when we find interesting anomalies, often it's a good idea to try and ask whether they can occur at the boundary of a higher dimensional system. And so in part two, I'll talk more about that bulk theory. And one of the things that I want to highlight is that you can think about these bulk theories and many of their unusual properties as resulting from the fact that they have a kind of quadripolar rather than dipolar Fermi surface. So I'll say more about that later. Okay, so let me start by talking about this sort of funny higher rank analog of the axial anomaly. So let me just remind you what is the axial anomaly. One way there's sort of two pictures that are nice and intuitive. So one is, suppose that we started with a scalar field theory that had this Lagrangian here, dt phi all squared minus dx phi all squared. Now, if you want to actually draw a picture of what's going on here, okay, you might think of this as the bosonic description of the low energy degrees of freedom of some, one-dimensional sort of metal. Okay, so here's its band structure right here. And of course, this Fermi surface has two parts. It has a part over here where we have right movers, and it has a part over here where we have left movers. Okay, so this picture here and everything I'm going to say about this picture here, we're going to be able to visualize in terms of this band structure. Okay, now let's look at this action for a minute. Classically, it has two conserved densities, the total charge density, right, which is basically the number of right movers plus the number of left movers. And also, the total momentum, which you can relate, just via the Fermi momentum, total momentum density to the difference between the number of right movers and number of left movers. Okay. And so, these two conserved densities boil down to two conserved currents at the classical level in our Lagrangian. So there's the electromagnetic current, right? And so this is, for those of you familiar with bosonization, this is the familiar density operator that we always write down, okay? And here's the corresponding spatial component of the current. And you can see that this current is automatically conserved. It is always the case that dt of dx of phi is equal to dx of dt of phi. So this current, this action is conserved no matter what. And then there's another conserved current, which we'll call the axial current. And that basically has the kind of the x and time components switched. So here I can say the density is associated with dt phi, okay? And then the spatial part of the current is associated with dx phi. And this current is conserved, but only, classically, only because of the equations of motion, right? So it's conserved because dt phi all squared minus dx phi all squared is equal to 0. Okay. And so this second current, whose conservation depends on the equations of motion, is not conserved, even classically, if we apply an electric field. Because if we apply an electric field, by coupling in our gauge field like this, that modifies the equations of motion, okay? And you find that actually d mu of this axial current is proportional to EX, right? And there's this picture here, which I think most people are probably familiar with in terms of the band theory, which is here was our left moving branch and here was our right moving branch. And then we apply an electric field. And what does that do? Well, that sort of moves the Fermi level, to the right in both the left and the right branches. Okay, and consequently, it looks like you've lost 2 fermions here and you've put them over here. Okay, so this is, I think, quite familiar to most people, and it often goes under the name of the axial anomaly. Okay. And so the interpretation of this is that this second current associated with momentum density is not conserved in an applied electric field. And of course, we're not surprised because we know that, the electric field is going to accelerate our electrons. And so obviously momentum is not conserved in an applied field. Okay. And so, so now let me tell you about a similar anomaly, which and like I said, we're going to talk about this in the context of band theory, but the original motivation for thinking about this as an anomaly comes from basically fractonic models, or more specifically models with subsystem symmetry. And so let's think about an action that's very similar to the one that we wrote down. I have a dt phi all squared, but instead of just dx phi, I'm now going to go to 2 + 1 dimensions, and I'm going to write down a kinetic term dx dy phi all squared. Okay. So again, this is some kind of free boson theory, but it's got a very unusual dispersion relation. In particular, this dispersion relation has lines of zero modes. Okay, because we have omega squared is kx times ky all squared, and these lines of zero modes are there because this model has subsystem symmetry. In particular, you can see that actually I can shift phi by any function of x or any function of y, and that doesn't change this action. And so this is called a sort of subsystem symmetry of this model. Okay, now a funny thing about this model, which is going to sort of play in when we start trying to make a connection to 3D bulks, is that unlike what we're used to thinking, clearly here, an energy cutoff is not the same as a momentum cutoff, okay? Because we have these lines of low energy out to arbitrarily large momenta. And so that sort of changes a lot of what our intuition might be, at least when we apply a kind of continuum field theory perspective. Okay, so like I said, it's a Lagrangian for a system that has some kind of, for a free bosonic field with subsystem symmetry. And so what Nadi Seiberg and collaborators pointed out is that this model also has 2 classically conserved currents, okay? It's actually very closely analogous to the 1D example that we just did. And so one current, the analog of the electromagnetic current, has as J0 this dx dy phi, and then so it's a 2-component current, and the spatial component we'll just call jxy, and that one is proportional to dt phi, right? And this current is again automatically conserved just because dt of dx dy phi is equal to dx dy of dt phi. And so by the way, this here dt j0 minus dx dy jxy, this is the appropriate current conservation law when we talk about these currents that couple to the gauge field appropriate to these systems, which is called a symmetric tensor higher rank gauge field. Okay. And so just like in the 1 + 1D example, so yeah, so let me not dwell on that, but just for people who haven't seen this before, this is a different current conservation law, but it is the one that's appropriate to systems with this kind of symmetry. Okay. And then there's a second conservation law, right? Where again, it looks like I've just kind of flipped the definition of J0 and JXY, okay? But again, you can check that this current where, J0 is dt phi and JXY is dx dy phi with a minus sign in this case. Again, this is conserved just because of the equations of motion. And so once again, we have 2 currents, right? The analog of the electromagnetic current, and this guy here is the analog of the axial current in particular. It's conserved only due to the equations of motion. And so once again, we're going to find that if we apply an appropriate external field, we're going to find that the equations of motion get modified, okay, and therefore this axial current is not going to be conserved. So in more detail, so again, because of this subsystem symmetry, the kind of external field that we're going to couple that this current naturally couples to, is not the familiar, kind of vector gauge field that you're used to, but it's a symmetric tensor gauge field in 2 dimensions. And so it couples to the current in this way with A0 times J0 and AXY times JXY, okay? And so when I add this coupling term here, the equations of motion are modified. And so I get this second piece, which looks a lot like an electric field, okay? Except, with just this dx dy. And so we call this the analog of the electric field. And so again, we have this sort of current conservation law that is where the current fails to be conserved, and that non-conservation is proportional to this modified electric field. Okay. And so this is the anomaly, right? There's an analog of this sort of familiar axial anomaly that occurs in these higher rank systems. And then the question that we'd like to ask is, this all seems very esoteric. Where in the world would we look for subsystem symmetry? This is a gauge field that, where did that come from? And so what we would like to know is, can understanding that this, kind of anomaly is here teach us anything interesting about much more familiar systems, notably systems that we can describe using band theory, okay? And, so let's start by taking a very naive approach, okay? And, the first observation is that it's certainly not hard to write down a Hamiltonian that has the same, kind of dispersion, if you like, the same lines of zero modes as the bosonic theory that we were just looking at, right? So here it is right here, psi dagger dx dy psi, okay? And so again, we expect that we're gonna have these lines of zero modes along kx equals 0 and ky equals 0. Okay. Now, this system is clearly different. When I write down some band insulator that just happens to have this dispersion here, it's clearly different from a system in which I'm thinking about, subsystem symmetry as being fundamental. In particular, here we actually have 3 conserved quantities, so the electromagnetic charge, and then, I have sort of 2 candidate momenta, momentum in X and momentum in Y. And so you might think, well, there's nothing here that's going to look like this higher rank current, and that's sort of true. Although, as we'll see later on in the talk, if I actually impose a sort of a reflection symmetry about the line y equals x, then these 2 momenta map into each other under that symmetry. And in that context, we actually will get some conservation laws that look very similar to the higher rank current conservation that I talked about a couple minutes ago.
Fiona, is this essentially a Van Hoff singularity or something like that?
At the origin?
Yes, because it's a place where the 2 Fermi surfaces cross, essentially. So it looks like a Van Hoff singularity.
Yeah, that's right. So away from the origin, you just have, if you like, stacks of lines with the Fermi velocity. But yeah, indeed here, if I sort of think about coming along this line at ky equals 0, here at the origin, the Fermi velocity is exactly 0. And that extends actually, out beyond the origin. So yeah, I think that's the right way to think about it. Okay. Okay. And so, yeah, so like I said, if you were just going to be naive and you want something that looks like it has the same dispersion, this is a natural thing to write down, even though you might be, there's no higher rank anything obvious floating around here at the moment. And so now let's take a look at the conservation laws. And so, if we have this kind of picture, so again, actually, let me take a minute to go back here. So let's focus on this line here at ky equals 0. And what's going on is that, so as Eduardo pointed out, we have a positive Fermi velocity in this direction here for positive kx. and then, sorry, positive sort of velocity in the ky direction here when kx is positive, and then a negative velocity, right, over here when kx is negative, okay? And so here, so I'm going to kind of draw that on this picture here. So at positive kx, everybody has different velocities, but basically these guys are all right moving in the y direction. And these guys over here at negative kx are all left moving in the y direction. Okay.
I have a question. I'm Andrea.
Hi.
Yes, but it's not completely obvious to me that this fermionic system has the conserved current you were showing before.
Right. So actually, hang on one sec. Let me.
So that's the first step of bosonization, right?
Yeah. Let me
write
just
the currents.
Yeah. So okay. So it has. Now, are you referring to the higher rank current or to the?
Yes, the one you showed before has this anomalous conservation law.
The JXY. No, right. So indeed. So I'm not claiming that it has that it has something that's exactly analogous to JXY. Instead of a JXY, which is a single quantity, what this system naively has is it has a current in X, momentum in X, and it has momentum in Y. Okay, so for now, we're going to think of those as replacing JXY. And then, later on, I'll say something about how if we actually impose this reflection symmetry, and particularly when we look at the bulk theory, we get something that looks very close, but they're not the same. This, in particular, the symmetries of this model are very different from the symmetries of the bosonic model that I showed before, because that model has a full subsystem symmetry, and any problem that you can realize as a band model where you're just thinking about fermion hopping does not have subsystem symmetry. Right. So, yeah, sorry. So very good. So does that answer your question?
Oh, keep going. Yeah.
Yeah.
Go
okay.
ahead, yes.
I'm sorry. I'm just going to shut this door. Robin, keep the kids out. Okay. Yeah. So now let's talk about conservation laws. Okay. And so as I said, the currents that we're thinking about being anomalous in this case are not.
Fiona, sorry, there is another question from the audience.
Yeah.
Just a short question. It seems to me that there is an additional symmetry where you scale X by some factor lambda, and you scale down Y by the same factor lambda. So shouldn't there be one more conservation law?
Okay. Yes, good. Okay, yeah. Yeah, that's a good point. I actually, to be honest, I have not thought about what that would correspond to. Now,
maybe it's broken by further terms in Hamiltonian that you neglect.
Yeah, well, so I think, if you're really thinking about this model here, this as a continuum model, it definitely has that symmetry. If you were thinking about something living on the lattice that lives in a Brillouin zone, then that would be, some deformation of the Brillouin zone. And so, so it wasn't something that sort of, that I had thought about just because we were sort of, well, as this has an interpretation in the bulk that'll be very clear, but yeah, what that would correspond to in the 2+1D continuum system, I actually have not thought about. But that's an interesting point. Okay, great. So yeah, so let's ask what happens to these momentum conservation laws when we apply electric fields. So as I said, I have right movers at positive kx, left movers at, in the y direction, and left movers in the y direction at negative kx. Okay, and so now what happens when I apply an electric field in the y direction, right? And so this is, you can think of this system for right now as just a stack of 1D systems at different kx, right? And these guys have, only, they're chiral. These guys are chiral with right movers, and these guys over here are chiral with left movers, okay? And so, we can kind of go back to our 1D picture to ask what happens, right? And so for the right movers, basically, we apply this electric field, and what we're going to see when we can just conclude this directly from our analysis of the 1D system at this fixed kx, right? What we're going to see is we're going to get, a creation of particles when we apply this electric field at this value of kx, but its partner at the opposite value of kx, we're going to destroy an equal number of particles, okay? So there's no issue with conservation of charge, okay? But unlike in our 1D picture where the right movers, and the left movers were, kind of attached by a single band, in this case, they're not, okay? And so what's happening here is actually that the momentum in X now is not conserved. So I'm basically, you can think of, it looks like I'm taking particles from negative kx and moving them to positive kx in spite of the fact that the field is in the y direction. Okay, and so this failure of this failure of momentum conservation is a little maybe more bizarre than what we think of in one dimension, where we say, well, of course, our electric field is accelerating the electrons, and so their momentum is not conserved. Here it's a field in y, and we're failing to conserve the momentum in x, and that's the thing that we're going to be worried about. Okay, and so that's our sort of analog of the anomaly, is momentum non-conservation. Now, there's another interesting thing that happens in this system. If we imagine putting it on the torus and we twist the boundary conditions, okay? So what I mean by twisted boundary conditions is that, so let me set this quantity delta to 0 for a minute. Let me remind you that when we do periodic boundary conditions, that quantizes the values of kx and ky, right? And they're quantized by the condition that, periodic boundary conditions, so e to the I kx times L had better be 1, and e to the I ky times L had better be 1, okay? And so now I can imagine sort of twisting this boundary condition by adding in my condition for x, some kind of twist delta proportional to ky, okay? So this is a boundary condition that I can choose, and when I do that, the allowed values of ky are 2 pi ny over L, and the allowed values of kx are 2 pi nx over L minus this shift here, okay? And so in particular, so this is kind of my picture here that, I go from delta equals 0, and then I twist all the way around to delta equals L, okay? And that twist basically shifts kx to kx minus ky, okay? And okay, so now before we were looking at positive and negative kx, but so now here, so the kx of each of these left moving states, can't remember if they were left moving or right moving in my previous picture, but let's call these guys left movers, okay? Their kx is going to decrease, okay? And the kx, and the kx of the states at negative ky is going to increase. But actually both of these things, right, are going to give us more fermions. And you can sort of see that because these guys are left movers, and so decreasing their kx, shifts my Fermi surface this way, okay? And so that's going to accommodate more electrons, and similarly here, if these are right movers, shifting the Fermi surface this way, it's going to accommodate more fermions. And so in this funny process in which I twist the boundary conditions, kind of do a full twist on the torus, I actually conclude that there's a process here that looks like it fails to conserve charge, right? So that's something we would be much more concerned with than something that fails to conserve momentum when we apply external fields. Okay, so this really does look like a system that has an anomaly, and unlike the axial anomaly in 1+1D, where the fermions, we know the fermions aren't really disappearing, they're just traveling through the band, and we know the electric field is altering their momentum and so on, and so that's actually fine. This is one that certainly looks like this is not something you should be able to do in a two-dimensional system. Okay. So that's the anomaly. Now let me come back to this question of how this compares to the higher rank anomaly that I talked about before. So in this case, we have a Lagrangian that looks like this. It has subsystem symmetry, and we were focused on two U1 currents, right? Which was sort of EM-like and axial-like, okay? And when we applied the analog of the electric field associated for this funny gauge field, which just has the two components A0 and AXY, so this higher rank gauge field, we applied the electric field and it violated that current conservation of this kind of higher rank analog of the axial current. Okay, and right. And you can also show, though we didn't talk about this, but you can show that you can define, there's a sort of dual picture of this in which you could define a gauge field associated with the axial current. And if you applied a flux of that, that violates electric current conservation. Okay, so I didn't talk about that, but this is exactly like you expect from the axial anomaly. Okay, so it's really an analog of that. In our fermionic system, really, we focused on three currents, right? We had charge, but then also momentum in X and Y. And we found that if we applied an electric field in X, it violates the conservation of momentum in Y. Okay, and similarly, if we apply an electric field in Y, it violates momentum conservation in X. And also that if we applied some kind of flux of, associated with this twisted boundary conditions, and we can think of that as a sort of a momentum gauge field, that actually gives us a non-conservation of the electromagnetic current, right? And so these look different, but like I said, if we, at some superficial level, if we imposed a reflection symmetry about Y equals X, we could think about the X and Y momenta as kind of associated with a single current related by a reflection. And in that case, these systems start to look similar. In particular, they both have this mixed anomaly between something that we would think of as a conservation law of charge and something that we would think of as a conservation of momentum, or this other axial current. Okay.
I have a comment, Fiona.
Yeah.
In lattice modes, for instance, the Hubbard mode, we actually free fermions on a square lattices at half filling precisely have Van Hove singularity like that. But they come in pairs.
Yes, indeed.
Okay?
Yeah.
So your non-conservation, essentially your gauge anomaly, the genuine gauge anomaly will be cancelled.
Indeed.
In that case.
Yeah.
So you cannot treat just one such singular point separately from the others in that sense.
Yeah, that's exactly right. Yeah. Well,
so in that sense, your anomaly is the gauge current now becomes non-anomalous as a result.
Yeah, yeah. And let me actually add one thing to that. So if you think about just these lines as being the Fermi surface, right? And it's not that we have the Hubbard model where, we have these, other points appearing at the corners of the Brillouin zone. But, if you just drew this, there's a very obvious problem in 2D, which is that the Fermi surface is not closed. Okay. And so I think that, if you don't impose additional sort of spatial symmetries, you could, basically, you cancel this anomaly anytime you close up the Fermi surface. So for example, I could close up the Fermi surface by kind of drawing a little circle out here, right? And a little circle out here. And it wouldn't necessarily be the case, actually, that I have to have other pairs of these guys elsewhere in the Brillouin zone. like, this circle could close, and it wouldn't have to close. If it closed at the zone corner, then I would have, another point somewhere else in the zone where I have this same kind of touching pattern. But it doesn't have to touch the corner, right? It could just kind of be two little circles, and you can actually write down a Hamiltonian that does that.
Right,
so,
but the last Hamiltonian will be non-local probably in this case.
No. I think, what it will have is these won't be straight lines, right? These will kind of curve around. But and I don't remember off the top of my head what the specific term is, but there is a term that that can be written down, so that you can tune, where you kind of have a little circle and then it goes out and they meet at the corners of the zone. So yeah, indeed, we would have liked a very sort of simple picture where it's like these things have to come in pairs, but once you allow the Fermi surface to be curved, that's not quite true. If you insist on straight lines in the x, of your Fermi surface in the x and y direction, so in other words, for example, if you insist that your Fermi surface be, invariant, under this, sort of certain, let's see, let me put it this way. If you had some, kind of symmetry that imposed that the Fermi lines have to sit on, high symmetry points like 0 and pi and so on, right? Then they have to come in pairs. But there's some extra symmetry, I think, required to force that. Does that? Yeah. Cool. Okay. Okay, good. And so, yeah, so as I said, there's an anomaly here. We should be worried about it because we can twist these boundary conditions and get something that looks like it fails to conserve charge. But also, obviously, this is not something that we could do in 2D because the Fermi surface is enclosed, right? And so now let's talk about what we should do to cancel this anomaly with the bulk. So what kind of bulk should we write down to cancel an anomaly associated with a system with an open Fermi surface? Well, of course, we know that open Fermi surfaces, in 2D occur on the boundaries of three-dimensional Weyl semimetals, okay? And so our bulk theory is going to be a Weyl semimetal, and what's different about this Weyl semimetal is going to be just the way that the Weyl points are arranged, where they have no dipole moment, but they have a quadrupole moment, okay? And so that brings me to part 2 of the talk, where I'm going to talk about quadripolar response, and specifically quadripolar response of Weyl semimetals in this case. Okay. And so so this is just a pretty picture. Let me just, remind you of the simplest sort of response that I think is usually the first thing that comes to mind when we think about Weyl semimetals, okay, which is the dipolar response. Okay, so in all of these pictures, so a Weyl semimetal here in the bulk has a couple of Weyl points. Okay, so we're not going to worry about like tilted cones and so on. So and this Weyl point has a chirality associated with it. And that chirality, if you want to compute it, you have to ask the question, is this Weyl node a source or a sink of Berry curvature? Okay, and so these sort of arrows going in indicate that this node has negative chirality, meaning it's a sink of Berry curvature. These arrows going out indicate that this Weyl point is a source of Berry curvature and it has positive chirality. Okay, and it's a fact that in a 3D system on a lattice, you can never have a net sort of chirality. So these guys always have to come in pairs. Okay, positive chirality and negative chirality. Okay.
Perfect.
Yeah.
Question. So when you have like a tilted cone, like a type 2 Weyl semimetal, don't you have this kind of Fermi surface with 2 infinite lines that cross?
In the bulk, you mean?
Yeah, I guess if it were a lattice model, at some point something must happen because you have an actual real line zone. But in the continuum, you would get this kind of picture, right?
You would, but it's in 3 dimensions.
Right. I guess for 3D. Yeah, I guess I was thinking maybe if you have a tilted cone in 2 dimensions, you would get this kind of Fermi surface, right?
Yes. Let's see. Yes, that's Yeah, that's right. If you took a Dirac cone in 2D and you tilted it, you would get this kind of Fermi surface. And then, but yeah, I think, yeah, that's right. And so, yeah, so now, you know, yeah, so you might say, well, let me say I don't care about time reversal. And so I'm going to start with, you know, graphene, and I'm just going to like gap out one of the Dirac cones and I'm going to tilt the other one. What happens? Right. But I think, you know, if you think about the way the bands are going, you can see that it's not necessarily that you have to create another point like this if you don't care about symmetries, but somehow or other that, you know, that Fermi surface is going to have to close.
But if you have like a tilted Dirac cone on the surface of a 3D TI, for example.
Yeah, that's okay. Yeah, that's an interesting question. But again, you know, right. So I guess the I haven't thought about that. The comment though that I would give is that if you don't have actually the Weyl nodes in the bulk, then whatever Fermi surface you're creating on the boundary is still going to be closed. So it's not going to have this same structure.
So it has to close somehow, I guess, if one thinks about it.
Yeah, yeah. I mean, I don't know how to get an open Fermi surface unless you have Weyl points in the bulk.
Okay.
Yeah.
Thanks.
So I think that's kind of the essence of what's different about this anomaly. Good. Okay. So yeah, so we have this pair of Weyl nodes in the bulk. And we're gonna kind of define the dipole moment, okay, of this Weyl semimetal by, so, you know, chi here is this chirality, and then alpha corresponds to the alpha Weyl point. So this is like the momentum vector, okay, at this alpha Weyl point, right? And so from that, I can define a kind of dipole moment of these Weyl points, okay? And it is well known, and I'm not going to kind of repeat the arguments here, but it's well known that if you have a pair of Weyl nodes, right, that on the boundary of my Weyl semimetal, I actually get an open Fermi surface or Fermi arc connecting a Weyl node of negative chirality to a Weyl node of positive chirality, right? And so this open Fermi arc is, you know, sort of like a stack of quantum Hall systems at a bunch of different momenta going between here. Okay. Good. And so now, once you have defined this dipole moment, it's cute and convenient that you can actually write down a nice theory of the electromagnetic response of the Weyl semimetal in terms of this dipole vector. And in particular, you can show that the charge density, and so you can ask what happens if I apply electromagnetic fields, okay? And if you apply a magnetic field, you induce some charge density, right? Which has this polarized dipole moment dotted with the magnetic field. And, oh, I'm sorry, this B0 should be P0. That's a typo, okay? And if I apply electric fields, let me not worry about P0 in this case, but if I apply electric fields, then I get, again, currents, spatial currents, and again, the sort of direction and magnitude of the currents depends on this dipole moment of the bulk Weyl semimetal. Okay. And so this is, you know, something that can be argued a variety of ways, but let me just sort of quote that result. And so, you know, so that means that I can write down this nice, so to get these kind of responses, okay, which you get, for example, the Kubo formula sort of calculation, you can now write down this nice kind of topological response theory, which looks like this. Okay, so this is the completely antisymmetric tensor. Here's my dipole vector here. And it looks like it's, you know, this dipole vector sort of crossed into this Chern-Simons theory perpendicular to the dipole vector, okay? And that gives me back, so if I take this action here, right, and subtract J mu A mu, so your standard coupling of your gauge field to currents, that will give you exactly the equations of motion. And again, I apologize, this should be P0, so you can define a kind of zeroth component of this polarization if you add chemical potential. that can be different at the two vial points, okay? And so this has exactly the right equations of motion to give back the electromagnetic response of the vial semi-metal. Okay, and so, you know, all you need to know for the purpose of this talk is that I can define this dipole moment of my vial points in the bulk, right? And that dipole moment determines the electromagnetic response, and we can encode those equations conveniently using this kind of topological response action, right? And now a convenient fact about this topological response action is that, you know, those of you who spend a lot of time looking at Chern-Simons theories immediately think to yourself, wait, this is not gauge invariant when I have a boundary. And that's actually exactly what we want. So this non-gauge invariance in the presence of a boundary actually tells you have to add these Fermi arcs, right? So this kind of line of chiral states, almost like a line of, so this is a sense in which this looks like a stack of, you know, sort of quantum Hall systems on the surface in order to cancel that anomaly. So this is exactly what you would expect. Okay, so that's the dipolar case. And now you can ask yourself, well, you know, what should we say? And, you know, what's for the bulk that's going to cancel the kind of surface anomaly that we have, which has this quadripolar pattern. Okay, so here again was a picture of our surface. We wanted to have these lines, and you know, this sort of structure of lines along kx equals 0 and along ky equals 0. Okay, and in order to get the right sort of surface response, it turns out that we need to line up the bulk vial nodes in this way. So the red ones here have positive chirality and the blue ones have negative chirality. And so we should, you know, really sort of think of our Fermi arcs as coming from here to here and from here to here, okay? And you could even round them out a little bit, and that's not so important, but you can sort of see that this has the right pattern of left movers and right movers associated with what I drew before. Okay, and so now let's ask a little bit about, you know, what this bulk theory looks like and what it does. And one thing I want to point out is that, you know, this bulk actually has time reversal symmetry, because time reversal actually preserves the chirality of the vial node. So it's going to take this guy over here and this guy over here. And so in the presence of time reversal symmetry, you necessarily get this quadripolar pattern because the dipole response of your system vanishes, okay? And so what that is going to tell us is that there's no net charge response to external electromagnetic fields, okay? And that's basically because the contribution to those charge response of these, you know, kind of time reverse pairs of vial nodes actually cancels. And so you can ask, well, what does this system do, this bulk system? It must have some kind of interesting bulk response, right? It's got this interesting pattern of vial nodes, but, you know, as I said, we write out the response action of vial semi-metals in terms of this dipole moment of the vial points, and that's 0 in this case. And so what that means is that, you know, the current response is 0, okay? But there is an interesting non-trivial response, which is actually a mixed response between the electromagnetic current and the momentum current, okay? And that one is not vanishing, okay? And so let me just sort of, so that one's not vanishing, and I'll give you what it is in just a minute, but let me first say that, so this J mu is just my usual electromagnetic current. This tau nu A, okay, is I literally obtain it from my band model by taking the nth component of the electromagnetic current, you know, dividing it by E and multiplying it by the appropriate, by K, okay, by K in the 8th direction at whatever value of K I'm evaluating this, okay? And so this is something you can just compute using a Kubo formula, and you find that these coefficients are not vanishing, okay? And you find that that these tau mu's, oops, and I can see I forgot to put the exact formula, but these tau mu's are proportional to the quadrupole moment of your bulk file nodes. Okay. And so let me, so that actually, okay. So let me just define this chirality. Okay. So this quadrupole moment. So to get the quadrupole moment of the vial nodes, what I do is I add up the chirality of each vial node. So alpha here is an index that indexes the different vial nodes. The K here is, again, the momentum at that vial node, right? And now we have to multiply 2 momenta to get this quadrupole tensor, okay? So the ith and the eighth in this case, momentum, okay? And so now what we learn from the Kubo formula is that, so, we can calculate these coefficients, and it's a mixed current momentum current response. And what that means is that if we want to understand what the electromagnetic response is, that's proportional to this quadrupole moment, okay? And then there's this piece here, which we should think of as a gauge field associated with the momentum current, whatever that is, okay? Okay, so this, and so, really, what gauge field should that be? That should be some gauge field associated with translational symmetry. Okay. And so what this means in practice is that, if I apply electromagnetic fields, I'm not going to see a net sort of charge density, current flow, et cetera, like that, when I add up the contributions of all of the vial nodes. But what you do get is an interesting electromagnetic response actually to certain lattice defects, okay? And so one of the things that this predicts is that if you have, for example, a screw dislocation, that's going to bind a charge. And so this is something, so you might think, well, okay, this looks a little bit, oh, oops. I think I was going to put in a picture that showed that. You might think, oh, that looks a little esoteric. So Oleg actually, verified this numerically, and you can put screw dislocations in your system, and you can see that you do get a charge accumulation on those. Seems like I forgot to put in the picture. Now, the other thing that this predicts, so this is again, a mixed current correlator, and the other thing that it predicts is a momentum current if I apply electromagnetic gauge fields, again, proportional to this quadrupole moment of the vial Fermi surface, okay, or the quadrupole moment of the vial nodes. And so, oh, sorry, somehow these two slides got mixed up. Yeah, so here is my, okay, right, good, sorry. So indeed, so when we apply electromagnetic fields, what we don't see a net current or net charge response, but we actually see a response in the momentum current or momentum density, okay? And so here's a picture, again, of this numerical verification. So you could put a pair of magnetic fluxes in your system, okay? And you can measure the momentum density at different areas, and you can see that, in fact, you get these, sort of oppositely bound momentum densities on these two flux tubes. Okay. And so, just as before in the dipolar case, all of this can be conveniently encoded in a topological response theory that looks like this. So here's my quadrupole moment, and here is, again, this kind of Chern-Simons-like term. Okay, now coupling the electromagnetic gauge field to this gauge field E, which is, the gauge field associated with our momentum current.
I have a question. That gauge field, is that like a field line?
Yeah. It's basically, it's closely related to that. So if you literally, what it is in a continuum version, right? And you have to be careful because we're working on the lattice, but in a continuum version, you can say, if I perform a general coordinate transformation, right? And then you can write, like, imagine you start with a flat metric, okay? And you can write your new metric in terms of like these E fields, like G mu nu is equal to A to AB, E mu A, E mu B, or whatever. So it's literally those guys, yeah.
So in the case of the screw dislocation, this will be how the frame that defines your wild node is actually changing, essentially? Is that an interpretation?
Yeah, that's right. Yeah, that's right. Yeah. Except, yeah, so there's a singularity, obviously, because it's a screw dislocation, but yeah. And indeed, they have, like, you can define kind of analogs of electric and magnetic fields, and their fluxes, measure the presence of lattice defects. Yeah. Good. So, right. So we can write down this topological response action. And again, okay. And so now this looks kind of like a mixed Chern-Simons term between the electromagnetic gauge field and these lattice gauge fields. And again, if we just take this and add sources, our equations of motion give us back exactly the response that we got from the Kubo formula, okay, which is very sort of concrete and standard way of calculating responses. So this is sort of telling us something that we should take seriously. And so, okay, and so we have this nice topological response action, and you notice the coefficient is the quadrupole moment, okay? And so just, in the last couple of minutes, let me connect this topological response theory to, something that actually is connected to this higher rank anomaly that I described earlier on in a very sharp way, okay? So let me suppose that I'm gonna, have this mirror symmetry about x equals y, okay? So I'm going to that in that case, this quadrupole tensor actually only has a single component, okay? Which I'm going to call Q, okay? So QIY and is equal to minus QXX, QXY has to be 0, okay? And this guy I'm going to call Q. And so then if I take this topological response, and I'm going to kind of write out some different components, okay? And I have an AZ times, and so now these epsilons is the analog of the electric field for this E gauge field, my translational gauge field. This calligraphic B is the analog of its magnetic field, okay? And so basically what I have is I have the Z component of my electromagnetic gauge field, and then I have the sum of this sort of epsilon YX and epsilon XY, okay? And then the other term I want to highlight for you here is I have A0, and I have the difference between BYY minus BXX, okay? And then I have two other terms here. Now let me not worry too much about these terms here, but let me replace this quantity, this EYX plus EXY, in terms of epsilon XY, okay? And so for those of you who are familiar with symmetric tensor gauge fields, this is a sort of a natural thing to do, but let me not get into that, okay? And I'm going to call EXY analogously this symmetric combination here. And so now I can rewrite my action, and here I have this piece here, this first line AZ epsilon XY minus A0 DZ EXY. And now this looks exactly like a symmetric tensor gauge theory, okay, coupled to a rank 1 gauge field. This second line here contains the remaining terms, okay? And I should say that, on all of my fields, I'm going to impose this reflection symmetry. Okay, and so now this action again, so I have these two lines here, and again, this action obviously is gauge invariant only up to a boundary term. And let me look at the boundary orthogonal to Z, for which only the first line actually contributes to this gauge non-invariance. And so if you look at that first line here, describing the boundary perpendicular to Z, okay, you can actually show that, so you can write out, what happens to this under gauge transformation, okay? What happens to this? So, gauge transformations of A, gauge transformations of E. You can write out, what is the anomaly of this theory, and you can convince yourself that actually these two exactly cancel each other, okay? So this is the appropriate bulk to cancel the anomaly of this subsystem symmetric SBT, okay? And we obtained it from the effective response theory of our Weil semi-metal, by imposing some extra symmetry and looking at a very specific cut of the boundary, okay? And so that's kind of, I'm not claiming that these two things are the same, but I'm claiming that, you know, we use this higher rank intuition, the knowledge of this anomaly, to look for an analog in fermionic systems, and that, you know, there is some kind of moral connection, even at the level of the bulk responses between these two systems. Okay, so it's not crazy to get your inspiration from these esoteric higher rank theories. Okay, and so maybe let me just sort of give you what I think is the take-home message for these quadripolar response, right? So, and this actually generalizes to other dimensions. You know, you can go down to sort of one dimension is very similar, two dimensions is a little different, but in both of those cases, you know, there's kind of a leading order electromagnetic response theory that depends on, you know, if you think about semi-metals, on the dipole moment of these Fermi points, okay? And when that dipole moment vanishes, actually kind of generically, what you obtain are, you know, not your standard electromagnetic responses, but rather mixed responses, where you have an electromagnetic response that cares about what's going on, you know, in terms of lattice defects and so on, okay? And those, you know, and the next leading order term that describes that response is the quadrupole moment of this Fermi surface. And then the interesting thing that we've talked about in three dimensions is that, you know, these quadripolar bulk responses can have boundary anomalies, indicating that you have these interesting surface states, right? And in this case, those resembled, though, you know, closely those that we encountered in the context of higher rank gauge theories. Okay, yeah, and so, oh, I think I have two slides which I might kind of just skip over just to say, yeah, so if you go down to sort of two dimensions, the analog of this polarization is actually not in the Fermi surface, it's the Berry curvature, okay? But again, you can get a kind of response in terms of the dipole moment of the Berry curvature, okay? And similarly to what we talked about in 3D, in two dimensions, you can actually get a Berry curvature quadrupole, and that has a different kind of response action, which also involves sort of surface flat bands with no net charge response, but a momentum response. So I'll just kind of flash these up here quickly, since I'm out of time, as something interesting where you can extend this quadripolar theory and talk about systems in two dimensions as well. Okay, and let me just put up my summary, and I think I can, you know, sort of, I think the main thing that I wanted to emphasize was this interesting chiral anomaly and its connection to quadripolar responses in 3D, and I'll just leave up this summary and take questions.
Okay, thank you very much for the nice talk. Let's see if we have questions from the audience or from Zoom. Yes, no, that's a clap, not a hand, because it's banded. I have learned these days. So if the hand is upstairs, this is a question. If it is rightly banded, this is a clap. That goes like this, okay? Well, I have a question. May I ask a question?
Sure, yeah.
Yeah, so you're saying that if I take a vile semi-metal and I work out the case in which I have time reversal invariance, you're telling me that on the boundary I should have these low energy modes with restrict mobility?
No. So indeed, yeah. So the subsystem symmetry, which is kind of the starting point for the bosonic model, that's never there in fermionic systems, right? So what I thought was interesting was that, you know, you can study these subsystem symmetric systems and you find, you know, they have qualitatively different behavior in a bunch of ways, right? So they have different anomalies, they have, you know, much different sort of coupling to, say, lattice response and so on. And so I think for me, the moral of this story is not, you know, not that we can sort of realize something that really has subsystem symmetry and free fermions, but rather that the kinds of phenomena which certainly from the point of view of thinking about continuum field theories are very different in these higher rank systems. Those kinds of phenomena, you can then come back and say, well, is there something that, an analog of this in free fermion systems that are completely familiar, that, if you kind of frame them in this new way, you see that actually, they have some similar phenomenology. So that, that was sort of more what I wanted to advocate for. Restricted mobility, you need a Hamiltonian that's quartic, actually, right? You can't, because otherwise you can't sort of have the right conservation laws.
So the short answer to my question is no.
Yeah, that's right.
Okay. Okay. So are there more questions?
I have a question.
Please.
Comment, actually. So a system, an electronic system, or in general system, where there is a traceless symmetric tensor that has an expectation value is usually called a nematic.
Yep.
Such as, the molecules that enter our computer screens. Okay? And in particular, there are many examples of electron nematics that have, for which this traceless symmetric tensor has an expectation value. So you're saying that if you have essentially a wild semi-metal that somehow became nematic, this is automatically going to have this sort of quadripolar response. Is that what the nematic response essentially is what this is?
Yeah, that's a good question.
I can say something.
Yeah, go ahead.
I mean, the degrees of freedom are dipoles, but the type of response you find that Fiona found is sort of Chern-Simons type terms in the response. They have nothing to do with the response of a real nematic phase in which you have in general a quadratic effective action. So it's completely different. I mean, the degrees of freedom might be similar, but the dynamics completely different because Fiona is finding some Chern-Simons terms, not ordinary Maxwell terms, to say.
I don't disagree with you. I agree. So that's why I asked whether in the context of the wild semi-metals, a nematic phase necessarily has this character. I mean, I want to think of this operator Q as being the expectation value of some dynamical degree of freedom.
Right. Well, so does being in a nematic phase mean that the kind of dipole contribution vanishes? Or like, are you thinking of a...
There is no dipole because that will give you a preferred
right.
orientation.
Oh, I see. Yeah.
A nematic gives you preferred directions, not orientations. Okay. So it's invariant under 180-degree rotations.
So what's ordering nematically like the...
I mean, you could have a spontaneous distortion of a Fermi surface where it becomes an ellipse, and that's nematic.
Right. Okay. So something
that will not break the reversal symmetry, as there will be no Chern-Simons terms. But the problems you're studying, you could have a situation where at the quadratic there is no quadratic term, but there are higher order terms that are present, as you say.
Yeah. So I would say I broadly agree with that when we talk about quadripolar response, presumably it's the leading order term in the nematic response. I haven't.
What happens with resistance if you apply strain in one direction?
Yeah, very good.
Which is essentially another way. That will couple linearly to this quantity Q.
Yeah, exactly. So yes, and so the answer is that we do expect, because this E field, right, is going to care about that strain, and so we do expect a response in that case as well, which is given by this quadruple response. And that's something that we're looking at, but I actually don't want to, I don't want to say I'm confident about exactly what you should write down yet, because there's a little bit of subtlety in how exactly what exactly the external strain should correspond to in terms of these E fields.
Does anyone try to do uniaxial strain experiments in 1 centimeters to see if this effect is seen?
Not that I know, but maybe somebody else can comment on that. If anyone else is connected into the experimental community here better than me.
Pardon my French.
Okay, so I think we can. You have there is a question by Michele Burrello. Just a second.
Hi. Concerning the quadrupolar response in the Weissman-Metal with time reversal symmetry, does the shape of the Fermi arcs or their connectivity play any role in determining the quadrupolar response, or is the quadrupolar response something universal?
Yeah, good. No, so the specific, and maybe let me go back to a picture here. Yeah, so indeed. So I think your question is like, do you care whether you have this actual sort of singular crossing point, or could I just draw the Fermi arcs like this?
Yes.
Or like this? Yeah, so no, indeed, the bulk response does not depend on that. So you can certainly and in fact, if you look at what the surface is doing, this crossing is a natural way to think if you are sort of imagining this dx dy kind of dispersion relation. So if you want to kind of think of it as an anomaly that's similar to that of something with subsystem symmetry. However, even if you draw these with curvature, okay, so, hopefully you guys can see my mouse. I draw my Fermi arcs like this. You can still convince yourself that if you apply an electric field in Y, you're gonna, you just look at this surface, you're gonna get non-conservation of momentum in X, right? So there's this, basically it is still this kind of stack of chiral things when you look at the, kind of the Y direction as a function of X, and it still has this funny, rather than the usual chiral charge response, which we would see with a single Fermi arc, it has this chiral momentum response, basically. And that's what's characteristic of this quadrupole bulk in terms of the surface. But yeah, the bulk response does not care about the details of how these guys are connected.
Okay.
Yeah. Can I ask a quick question?
Of course, yes.
Oh, thank you. Yeah. So in your definition of your momentum current, you had this K, right? But was that only for the continuum, or because on the lattice, then K becomes a crystal momentum, so it's a compact variable. So shouldn't it be a periodic function of K?
Yes. Yeah. And so, yeah, very good. So, yeah. So in terms of the Kubo formula, I don't think, I think which is where, so this is the definition that we used in the Kubo formula, right? Sort of, you can compute that on the lattice. I don't think that the periodicity of K makes a huge difference here, but it is important. So if you kind of look at these response theories, so this periodicity of K, right, and the fact that this current is actually periodic, where does that manifest itself? At kind of at the more abstract level of these topological response actions, it manifests itself in the sense that lattice gauge fields, we shouldn't really think of them as being U1. They're actually these, usually when you write down lattice gauge fields associated with lattice response, they're discrete. Okay?
Right.
And so if you think of them as being discrete, then that does, when you ask about anomalies in terms of like anomalies to the lattice response, that is important because discrete and continuous, it does not have the same anomaly. So for example, you can go to one dimension, right? So there's, an axial anomaly in one dimension, there's a quadrupole moment of the one-dimensional kind of Fermi surface, okay? And this is, and there's a recent paper by Gaoya, Burkov, and Chong Wang, where they have a really nice discussion of this. But so the point is that you could write down an effective action that describes that, okay, and it looks like it's anomalous, but you have to be very careful because it would be anomalous if these lattice fields were U1 gauge fields, but you have to be a little careful because they're actually discrete gauge fields, and so those anomalies, the structure of the possible anomalies is different.
I see. I would have thought I thought compact versus non-compact, but you're saying it's continuous versus discrete somehow is the right.
I mean, well, okay. What I'm saying is the compact versus non-compact momentum at the level of what we calculated in the Kubo formula, I think is not so important, but it does. If what we got out of the Kubo formula was this where'd it go? Was this response action, right? And so here, if you want to analyze like the behavior of the system, okay, and the anomalies and so on, it matters whether you think of this E as being continuous or discrete.
I see.
Yeah.
Thanks.
I think Eduardo, do you have another question?
No.
Okay.
Okay. So let's thank the speaker again.